For today's lecture, I would like to discuss the moon, our constant companion. Whenever you look at the moon, one of the things that we first think about, of course, is the phases. Well, to thoroughly understand the phases, we have to understand the primary motions of the moon. As you can see depicted here, the moon does have both motions, revolution and rotation. For the moon to revolve a full 360 degrees, it actually takes 27.5 days. This is called a sidereal month. Okay, well, whenever the moon goes from phase to phase, so in other words, like from a new moon phase back to a new moon phase, this takes 29.5 days, and this is called a synodic month. We're going to discuss here in 1 second why we have those two different months, and why it takes two amounts of time, because we're not taking one motion into account. Well, whenever you look at the rotation, the moon also rotates on its axis, and it takes 29.5 days to make one complete rotation. So now that we have an understanding of the motions of the moon, now we're going to get into what actually causes the phases of the moon and how it relates to these motions. Okay, the first thing we have to explain is the difference between a sidereal and a synodic month. As you can see in this diagram, what we're going to do is we're going to basically establish a baseline. Okay, this baseline has got to be what are we determining upon, the sun, or are we determining it upon the motions compared to a distant star? So whenever you start looking at this, now remember, a sidereal month takes 27.5 days. A synodic month takes 29.5 days. The sidereal month basically is one full 360-degree revolution. So whenever you start looking at this, here's what you're going to see. You're going to notice that right here, we have the new moon, and for it to make that one 360-degree revolution, it only takes really 27.5 days. But for it to actually go one complete revolution from new moon phase back to a new moon phase, the thing that you have to take into account is the Earth's revolution. We move approximately 1 degree every day. So what you're going to be looking at is you're going to be looking at a change of approximately 30 degrees over the course of a month. Well, to actually look at that, 30 degrees is basically going to be equivalent to an additional 2.2 days. Okay, so whenever you start looking at this, it's because of the Earth's revolution around the sun that we're changing the position, and to get back to that new moon phase, it has to move an additional 2.2 days. Okay, so that's the primary reason for the difference in the sidereal and the synodic month. Okay, well, as the moon revolves around the Earth, it also changes the Earth-Moon-Sun relationship, resulting in different portions of the moon being illuminated. This is what we call the phases. For every single phase, it takes about 3.5 to 4 days before it to change on to the next one. Well, the phase we observe depends on where we are in our orbit and the location of the sun and the moon in relation to the Earth. Now, of course, this is sped up, and because of that, what's going to end up happening here is a lot of misconception can be construed that we go through the phases over the course of a day. That is not true. Remember, we go through the phases over a course of 30 days. All right, the next thing I want to discuss is the actual phases of the moon. As you can see, depending upon the Earth-Moon-Sun relationship, we're going to see a variety of actual phases. Starting on the left here, you're going to see what is called the new moon phase. The new moon is whenever the moon is directly between the Earth and the sun, and of course there is no illuminated side. That's why we don't see the phases of that phase of the moon. And as we progress through, what you're going to see is you're going to see that we go through the next phase is the waxing crescent, as the moon starts to move around the Earth and change the orientation of where it is in relation to the sun and the Earth. Well, then we're going to have our first quarter moon, as you can see here. And then we're going to have what is called our waxing gibbous. And then we're going to progress on to the full moon, and so on and so forth. So really what is responsible for the changing phases of the moon is really just the change in position of the moon in relation to the Earth and sun. And what we're seeing is we're seeing a different illuminated side. And again, as you progress from new moon back to new moon, it takes approximately 30 days for that to actually occur. Okay, so these are your phases of the moon. And what we're going to do is we're going to look at how do we distinguish each phase as we look in the night sky. So one of the first things you want to look at is you want to notice that, okay, we want to be able to differentiate, that is, between waxing and waning. Well, this is actually rather simple because all you do is you look at the side that is illuminated. If the right side is illuminated, you're in a waxing phase, and if the left side is illuminated, you're in a waning phase. So of course, right here you have your waxing crescent, first quarter, waxing gibbous, then we go to our full moon, and then you go to your waning gibbous, third quarter moon, or last quarter sometimes referred as, and waning crescent. So by looking at which side is illuminated, we're able to distinguish is it a waxing or a waning. Okay, another characteristic feature of whenever we observe the moon, we never really get to see the far side. And the question is, why don't we get to see this far side of the moon? Spacecraft, of course, with the astronauts, were the first to see the far side of the moon and start to gather that data. But whenever we look up in the night sky, we only see the image that's on the left. And the question is, why? Why don't we get to see the far side of the moon? Well, you have to remember, the moon does rotate, but that rotation is synchronized with its period of revolution. Okay? So in other words, as it's rotating around, its period of rotation is equal to its period of revolution, so it takes the same amount of time, 30 days. For that, we never get to see the backside of the moon. Okay? Now, this is the actual revolution of the moon and the rotation of the moon. It has nothing to do with the synchronous rotation of the Earth. It has nothing to do with the synchronous revolution of the Earth. It has to do all with the motions of the moon. That's a key thing to remember here. Okay, another thing that you're going to notice is if you look up in the night sky and you're going to see the moon at different sizes. Well, this is what is called apogee and perigee. Now, whenever we start looking at this, just, some definitions here, apogee is not close to the Earth, and perigee is when it's actually close to the Earth. So what is that actually indicating to us? That's indicating us that the moon, much like the Earth around the sun, has an elliptical orbit. And because of that elliptical orbit, we're changing the appearance of the moon in the night sky. Okay, so there's the primary reason that sometimes you'll see these very large moons, and then there's other times that the moon is going to look much smaller, okay, because of its elliptical orbit. Now, whenever you start looking at this, a supermoon is the coincidence of a full moon or a new moon with its closest approach to the moon makes the Earth in its elliptical orbit. This is what gives it that really large size. So in other words, what you have is whenever the moon is at perigee and it's in full moon phase, okay, it's going to appear to be really, really large in the night sky. That's what we actually call a supermoon. Now, another one of the misconceptions that you're going to hear is you've heard of things called harvest moons and, of course, blue moons. A blue moon is nothing more than 2 full moon cycles in 1 month. That's kind of a unique thing. Of course, the 1 month that cannot happen in is February. But whenever you start looking at this, it's kind of starting to put all these motions together to kind of figure out why do we see what we see in relation to the moon. Okay, next thing that you're going to look at is all right, I'm going to go out and I'm going to look at the moon tonight. I want to see this certain rise time and I'm going to see a certain set time. Well, what's going to end up happening is through the course of the night, you're going to see the moon move across the sky, okay? And that moon is going to move, of course, from east to west, just like everything else. But what's going to end up happening with this is you're going to see it in one phase for approximately 3 to 4 days. And then you're going to see it transition into the next phase, and you'll see that for another 3 to 4 days. But the big thing here that you have to look at is you have to realize that whenever we go out to look at the moon in the same position every night, we're not going to see it at the same exact time. So in other words, if I go out and I see the moon tonight at 6 o'clock right along the horizon, I'm going to go out tomorrow night and I'm going to see that moon at 6:52. The reason being is that the moon actually moves along in its orbit 13 degrees per day because, of course, 360 degrees in a circle in its revolution, and one revolution takes approximately 30 days. 360 divided by 30 is 12 degrees per day, 13 roughly. And then what ends up happening is the moon is constantly changing positions. Okay? So what you're looking at is you're looking at trying to say, when am I going to see certain rise and set times of the moon? So the last slide talked about this 52 minutes later every single night. But then what ends up happening is because of the revolution of the Earth, it sets it back. So for the purposes of this slide, we're going to drop that 52 minute change that we've just discussed. And we're going to look at what would happen if and what time would we see the rising and set times of one phase of the moon. So let's go ahead and focus on the full moon right here. As you can see, the full moon is actually on the outside of our big picture here. We've got the sun to the right, the earth in the middle, and of course our moon over there. So the question is what time would we see a rising full moon and what time would we see a setting full moon? Well, the first thing you have to remember is the earth rotates counterclockwise. So this is the earth rotation direction. So let's go ahead and just basically say, let's start from right here, 9 a.m. Okay, so at 9 a.m., notice we are only looking at one phase. So this is the only phase that we would see. 9 a.m., I would not be able to see that phase. Noon, I would not be able to see the full moon. 3 p.m., I would not be able to see the full moon. 6 p.m. At 6 p.m., look at that. If you draw it, you're going to start to see that full moon right along the horizon. Then at 9 p.m., we're going to see it progress across the night sky and get higher. And then at midnight, what we're going to do is we're going to see the moon at its highest position in the sky. So again, that moon rose in the east, and now it's at what is called the meridian, its highest point in the sky. And then as we continue to progress throughout the night, you're going to get here to 6 a.m., and that's the set time of the actual, of a full moon. Okay? And then it starts over again, and we keep on going. Now, let's say we go about 4 days later, and now you're going to be what is called the waning gibbous phase. So now you're going to go out. We're going to say 9 a.m. again. Nope. Actually, let's start at noon. At noon, do not see it. 3, 6, whoa, right there. So at 9 p.m. is the actual rise time. At 3 a.m., it is actually going to be at the highest point in the sky. And then at 6 a.m., it's going to start to decrease. And then at 9 a.m., it's going to be setting. So because of the rotation of the Earth, the moon is going to progress from the eastern horizon to the meridian to the western horizon, and it's all due to this rotation. So depending upon which phase you're in determines what time this thing is going to rise and which time this thing is going to set. Okay? So hopefully that makes kind of sense to you. The best way to do it that I have always done it is just say whatever phase it is in, like first quarter, think of drawing triangles. If I can draw a triangle, there is my rise time, there is my set time, halfway in between is the meridian. So what this does is this explains why sometimes we can actually only see certain phases during the day, okay? Like that waxing crescent. That waxing crescent is seen from 9 a.m. until just about dusk, which is 9 p.m., okay? And then, of course, that is taking that 52-minute thing out of the equation. So that's what we're looking at there. Okay. Well, with that, this concludes our lecture on the mysteries of the moon. I hope you get a better understanding of the phases and what causes these. Our next lecture is, of course, going to be going over lunar and solar eclipses.